All right. Our next speaker is Xiqing, and from Purdue University. He's going to talk about NIC. I love these short names at the beginning of titles.
Thank you. Hello, everyone. Good afternoon. Welcome to my talk, NIC, Detecting Adversarial Samples with the Neural Network Invariant Checking. I'm Shiqing Ma from Purdue University. This is a joint work with my colleagues Yingqi Liu, Guanhong Tao, Wenchuan Li, and my advisor, Xiangyu Zhang. So adversarial samples in deep learning. Intuitively, adversarial samples are model inputs generated by the adversaries to fool the model inputs. A very simple example here. We have the legitimate inputs, and we feed it into the model, and we'll get the correct output label. However, if we use some attacks, we can generate the perturbations add to the original image, and we'll get the adversarial sample. If we feed this into the model, we'll get the wrong output label. And this is the adversarial sample. Even though for humans, they look very legitimate, however, the model doesn't really recognize this. There are many existing adversarial attacks. For example, we roughly classify them into two categories. The first one is semantic-based perturbations, and the second one will be pervasive perturbations. For the first category, they mainly will modify a region or some regions of the whole image to simulate some of the real-world scenarios, such as watermarks in the image. And for the other category, they can alter the image in the pixel level. Usually, they will measure the perturbation by different distance metric. Usually use the LP norm, such as L0, L2, or L infinite. Here are some representative attacks for the two categories. For the first category, we have the dirt attack, which tries to simulate the camera lens are dirty. They have a lot of dust. And some of them use the brightness attack. They can change the whole image color to simulate different lighting conditions. Some of them, the rectangle attack, to simulate the camera lens are blocked by some other objects, such as a paper or something else. And also the children attack, which adds some small patches into the image to simulate watermarks. And for the other type, we have a lot of work, including the FGSM, BIM, and the CW attacks, the Deep4 and GSM, etc. We also have many detection and defense mechanisms. Because NIC is a detection mechanism, I'm only going to show a few detection methods here. The first category will be trying to characterize the dimensional property of the adversarial regions, such as the lead work from iClear 2018. And the other category tries to use denoisers, which essentially are other machine learning models which can remove or reform the perturbations so that the perturbation can be easily detected by the original model, such as ImageNet from CCS 2017 and HGD from CVPR 2018. HGD actually won the first place in the NeurIPS 2017 competition on defense against adversarial attacks. And also the last category will be the prediction inconsistency, such as feature squeezing from NDSS 2018. It predefines a few squeezers, applies them on the original image, and feeds all the images to the model and compare the results to see if they are consistent. If they are consistent, they will say this is not an adversarial sample. Otherwise, it's detected as an adversarial sample. However, we did a lot of experiments, and we found that most of the existing detection methods only work on a small set, a subset of the existing detect or data sets. We will show some of the evaluation results later. Other researchers actually also found similar results. I'm quoting the sentence from one paper will be published in Auckland 2019 this year. It says all the detection methods show comparable discriminative ability against the existing attacks. Different detection methods have their own strengths and limitations facing various kinds of adversarial samples. This is not new phenomenon in our security research. We have seen many cases like this. For example, we can have many control flow or data flow hijackings to redirect the execution of a program, and we developed many defense mechanisms. The defense mechanisms doesn't really work on all of them. So this leads us to thinking, how about we can learn some of the experience from them, and we can use their philosophy, their successful experience to guide us design more general detection mechanism. Our method is inspired by the program invariants. How does program invariance work? Here is a very simple example. This is a Fibonacci number computing program. Line 2 is a value invariant. It checks the given parameter has to be larger than or equal to 0. And line 3 is a control invariant. It asserts that this function, the caller of this function has to be its own, meaning a recursive call, or it's from the main function. So the key idea of using program invariance is to use the invariant checks to only allow the correct behavior of the program execution and disable all the other possible malicious behaviors. We observe that DNA execution are just like program executions. So you have the input layer, get the input data, and in the next few layers, you just get the data from the previous layer, apply the matrix computation activation function, and then pass the data to the next layer. So we propose two types of DNA invariance. The first one is also the value invariance. It tries to model all the possible neural value distribution of each hidden layer. And the other one will be the provenance invariance, to model the possible neural value patterns of two consecutive layers. If one input violates one invariant, it will be detected as an adversarial sample. So the first type will be the value invariant. We all know that the pre-trained model have very good results on the training data and some of the testing data, meaning that the pre-trained model can actually well recognize the distribution represented by this training data and the testing data. But they don't have a good performance on the adversarial samples, meaning that they can't really capture the characteristic of these distributions. And these distributions are represented by the internal neuron activation patterns. So our value invariant are proposed based on this very simple observation. The perturbations will change the activation patterns in the hidden layer. We found that many attacks actually violate the value invariance, and most attacks will actually generate their own new activation patterns in the hidden layers. So we propose the value invariants, which are essentially trained classifiers, which can capture the activation pattern of the benign inputs in each hidden layer. Here I show some examples of the attacks which significantly violates the value invariants. To train the value invariants, it's very simple. We first just dump all the neural activation values using all the training data and the known test data, and then train a classifier. Because we don't really have the adversarial samples, so we just use a one-class classifier to train them. In practice, we use a one-class SVM method. Value invariant is not enough. For example, if we input this digit 1 image, we get a set of activation patterns. If we input another image 0 here, we can get another set. If we patch the digit 0 image into this digit 1 image, even very small, in many cases, we'll get the different result, sometimes even random label. And we inspect all the internal neurons, and we found that in some layers, it is very similar to one of the output label, but in other layers, it changes focus to some other parts, which will lead to another different label. So based on this observation that the DNA model will focus on different parts in different layers, so such as the previously shown image, the patched image looks similar for layer 1, but very differently, similar to 0 in layer 2. So we think that using individual value invariants is obviously not enough. And then we propose the provenance invariant, which we try to capture the activation patterns across different layers. And these are some of the attacks which usually violates the provenance invariants. How to train the provenance invariants? We originally tried to train them on the original neuron activation values, but found the space is too huge. There are too many of them, and it's very hard to train. And then, so we first perform lower the dimension of the individual layers, and then we concatenate two consecutive layers into one sample, and then train one-class classifiers to get the provenance invariants. And here are some evaluation results. For the hardware, we use 2 servers with a lot of memory and some GPU cards. As a comparison, we compared with aforementioned methods, including LID, ImageNet, HGD, and feature squeezing. For the datasets, we tested on MNIST, CIFAR10, ImageNet, and LFW. All the models are also downloaded from hardware, and they are very well used in other papers as well. For the attacks, we tested on FGSM, BIM, the 3CNW attacks, Deep4, GSMA, the semantic-based perturbation attacks, the dirt, brightness, rectangle, and children attack. The attack parameters are also adopted from previous papers, so I'm not going to skip all the details here. Overall, we found that NIC can actually achieve over 90% detection accuracy on all the attacks. And other methods doesn't really, they achieve very good results on a subset of them, but not on all of them. For example, the lead method is very good at the L-infinite attack on the MIST and CIFAR, but it has poor performance on large data sets, such as ImageNet. As shown here, for some cases, the detection result is less than 80%. And for the magnet, we found that it doesn't really perform well on some of the L0 and L2 attacks. For example, for the GSMA on the CIFAR, its accuracy is only, its detection rate is only 74%. We also found it's kind of hard to train the denoisers on the large data sets, such as ImageNet. So we compared the ImageNet with another method, that's HGD. That's a denoiser. They proposed a new architecture to train these denoisers to remove the perturbations. But the result found that it doesn't really work well on some of the L2 and L0 attacks. The detection rate is around 80%. And lastly, for comparison with the feature squeezing, the original paper already mentioned they don't have a very good performance on the ImageNet for some attacks like FGSM. It's only around 40. We also found that the performance doesn't really work well on some of the semantic-based perturbations like brightness attack, because we suspect it's because of some of the predefined squeezers don't really have a very good performance here. And for some other results, I will just quickly go through them. For one-class classifiers, we tried many of them, and we found OSVM is the best one. And for value invariants and provenance invariants, if you just use one of them, the performance is not optimal. So we have to use both of them. They are complementary. For adaptive attacks, we also tried this, and it's based on CNW2 attack. And we found they can achieve nearly 100% accuracy on MNIST and CIFAR10. And the distortion is slightly higher than feature squeezing. We have also a bunch of other results in our paper. If you are interested, please read the paper. As a conclusion, we propose the DNN invariant-based adversarial sample detection method, NIC, is inspired by the program invariants, and it only needs benign training data. We don't need the adversarial sample to have this method, and it's able to detect a relatively large set of existing attacks, and it achieves a better performance on all the comparing with all the work we compared with. And it increased the bar for adaptive attacks, but still we admit that we are still vulnerable to adaptive attacks. So as a next step, we may want to improve the quality of these invariants and also try to deal with adaptive attacks and also try to harden the model instead of just detecting the adversarial samples. And thank you. I'm happy to take questions.
Hi, Nicholas Carlini, Google Brain. Are you planning on releasing source code for your model?
I released all the models, but some of the source code I need to clean up. Yeah.
Okay. Do you know when you'll release them by?
I think after my job hunt.
Good answer.
By the way, I'm on the job market. Thank you.
Hi, I'm Chen Feng from Siemens Corporate Technology. I have a question about the false positive rate of the classifier. You didn't show this. I imagine that because you use OCSVN to find the invariants, and what if you have some new pictures or samples, then it's not in your training set? Can it be misclassified as an adversary sample using your method?
That's a very good question. We have the related data in our paper, but I can't recall the concrete numbers. I think we reported the false positive rates and everything.
Okay. Okay.
Thank
so
you.
I can see it from the paper.
Right.
Oh, cool. Thank you.
Huiying Li from University of Chicago. I wonder during your experiments, how many layers are you using for the invariance checking?
Actually, I use all the layers, but later after I can do some optimization. I found for some invariants, like the value invariants, the max polling layers are more important. Sometimes the convolution are less important. I don't have a after optimization results, but not a lot really.
And also, I read your paper, and in your paper, to reduce the dimension, you said you need to retrain models. So in this case, you have to retrain one model for every single layer, right?
I think you may have some misunderstanding. We don't really retrain the models. We just
not
get
retrain the whole model, but you have.
We get the value, but we use softmax to perform because softmax is essentially a normalizer. It normalizes the high dimensional space into the probability distribution, makes things easier. But you can use other methods like PH or other methods. It's fine.
But if it is an intermediate layer, you cannot just link it to the input layer, right? You have to contain the previous layer.
Right. That's right. That's why what I said is dump all the activation values and then apply the analysis.
Okay.
I use the normalizer to normalize to a probability distribution, which also lowers the dimensions.
Thank you.
No problem.
I'm Bimal Vishwanath, Virginia Tech. So, numbers are very impressive. I mean, there is no room for improvement. It's 100% in many cases, right? So, my question is, are we there? I mean, in terms of detection or defense, it seems like it's almost based on the numbers I saw, right? That's one question. The other is, I'm a little, I'm confused that you use this provenance-based mining approach, right? You try to find patterns in the data. Across layers, but some of the models you use are very complex, and they're not even feed-forward networks. They have short circuits and all that. Could you say how you overcame those challenges? For example, Inception V3 models and so on.
Okay. So for the first question, I think essentially we are not there, as shown before. I think the more challenge lies in the adaptive attacks. If you know the attack methods, it's kind of easy to detect them, right? But adaptive attack means if the attacker knows the adversarial strategy, he can develop more advanced attacks and then hack into your system and make the misclassifications. And for the second question, I think there are a lot of challenges, including different model structures like ResNet and Inception, all that. But the overall strategy for me is I try to view them as individual units and model them as a kind of standard structure, such as Inception net. It has a few branches, right? But I only take the merge points and then train the invariants.
Okay. Just one quick follow-up. So somebody asked about false positives. So are false positives low or high?
I have to admit, for some cases, it's kind of higher than expected. Like I remember for ImageNet, for some cases, is around 18%. Which I personally think is pretty high.
Okay, but shouldn't that numbers be shown along with the recall that you had? I mean, that would give a better idea about how your model is performing. Because right now it seems like it's a perfect detection scheme, which is not.
Right, because due to the time limit, I can't really show all the results, so I present the part of the result here. But most of them, you can find all the results in the paper.
Thank you.
Hi, sorry for this long question session. So my name is Anthony Lopez. I'm from University of California, Irvine. I'm not an expert on machine learning at all, but I'm curious. It's not related to security, what is your opinion on the value invariants that you found? Could you use them for transfer learning by any chance? What is your opinion on that?
That's a very good question. We actually are currently thinking, different applications of these invariants. We try to interpret if we can really understand these invariants. And we actually have another NURBS 2018 spotlight paper. It's from the inspection perspective. Also extract some of the hidden layer patterns and try to see if they can be used to detect adversarial samples. This is one case. And for the other one, we try to see if we can really, harden the model by encoding the invariants into the model itself. So we won't be just detect the adversarial samples, but really harden the model, makes it more robust.
Just quick follow-up. Actually, it does relate to security, but I know they're using machine learning a lot in, I think, traffic patterns or this kind of a malicious behavior online.
Mm-hmm.
Do you think this invariance could be used for that application too?
I might be optimistic, but I think so, yes. Even though I don't really know how to do it for now, but
Yeah, I was just curious. Thank you so much.
Thank you.
Shan from University of Chicago. So I just have a question about the adaptive attacks. So for adaptive attacks, do you think adding more invariants or things like that will solve the problem? I think for attackers, they can always know the things you added, and there's yes, of course, you can reduce the attack space of the attacker, but they can always put more power and get successful attacks.
That's a very good question, actually. So I think currently people tend to agree that the original model have very high accuracy because it's trained on the IID data. And why it's not robust is because the distribution shift. So in order to make the model more robust, you have to deal with this kind of distribution shift. Detecting is not, it's just one step for us to really understand, what's happening there. But I think really hardening the model to make it to be robust to this distribution shift will be the ultimate goal.
Thank you.
Thank you.